After completing the process of forming the required response surfaces based on the appropriate model, the results related to the response surfaces are presented in different formats of response points, min or max search, and charts. Also, the charts has different formats of a standard 2-dimensional and 3-dimensional. Also, the 2-dimensional slices, local sensitivity bar or pies, local sensitivity curves, and spider charts. This figure shows the sections that provide the final results of the response surfaces created in the ANSYS Workbench software. After the response surface production process is completed, the response surface is estimated using the design points in the DOE. This surface of positive response involves several points. In fact, each of these points on the response surface has values of each of the input parameters, and thus the design point can be defined by defining the desired values for each of the input parameters or variables in the range of its changes. A new design point than the ones generated in the test environment or DOE can be created. As a result, obtain the value of its desired output parameter at this new point. Suppose, for example, that the two output parameters change as the temperature outlet and the outlet mass flux, based on the variation in three input parameters as the length, geometry, radius, and velocity are investigated using the response surface method or RSM. The range of geometric length changes from 720 mm to 880 mm, and the range of geometric radius changes from 90 to 110 mm, as well as the range of flow velocity changes from 0.0009 to 0.0011 meter per second. This figure shows the response points which can be generated by tapping any desired value for each of the parameters of radius, length, and input speed to generate a new design point. Then the output parameter value and the discharge flow rate were obtained. Two types of optimization are performed automatically in terms of maximum and minimum values on each output parameter. This means that maximum value and the minimum value are defined for each output parameter. These optimization steps are based on response surfaces from design points and will have reliable results. This process takes a short time, but it can take a long time if the discrete, fictitious, or manual values are defined for input data or if number of output parameters is too large. In general, this section can provide the minimum and maximum of each of the defined output parameters. In fact, two sections, the minimum output parameter and the maximum output parameter value, appear in tabular form. In this way, it determines which of the input parameters for which values the desired output parameter reaches its maximum or minimum value. Also, the maximum and minimum values obtained for each output parameter in the house whose row and column represent the same output parameter are displayed large and colored. Suppose, for example, that the two output parameters change as the temperature outlet and the mass flux outlet flow, based on the three input parameters as the length, radius, and velocity. The velocity inlet input is checked using the response surface method or RSM, and this figure shows the table for the maximum and minimum values obtained from each of the two output parameter variables and the output mass flow. The two-dimensional diagram shows the changes in an output parameter in terms of changes in an input parameter. Thus, the horizontal axis or x-axis represents one of the selected input parameters, and the vertical axis or y-axis represents the change in the desired output parameter. In the three-dimensional diagram, the change of the output parameter are shown simultaneously according to the change of the two input parameters. Thus, the two axes of the screen x-axis and y-axis represents two defined parameters or input variables, and the vertical axis or z-axis represents the change in the desired output parameters. In both cases, drawing two-dimensional and three-dimensional diagrams, when the graph of change in an output parameter is plotted according to one or two input parameters, the values for the other input parameters defined in the process of creating response surface method or RSM that is not used in the drawing chart must have a fixed value, so that this value can range from the minimum value of its change period to its maximum value and can be defined manually. Suppose, for example, that the changes in an output parameter called temperature outlet are examined in terms of change in an input parameter called the length of the geometry using the response surface method or RSM. Also, the other input parameters are equal to a constant value equal to their average value in the range of their changes. This figure shows the change in output parameter, output temperature in geometric length. Now, suppose that in an example, the changes of an output parameter called temperature outlet are investigated by changing the two input parameters as the length of the geometry and the radius of the geometry using the method of response surface or RSM. Also, the other input parameters are equal to a constant value equal to their average value in the range of their change. This figure shows the changes in output temperature in terms of geometry, length, and radius. The changes of one output parameter are shown in simultaneously according to the changes of two input parameters. Thus, a horizontal axis or x-axis represents one of the two defined input parameters. A vertical axis or y-axis represents changes in the desired output parameter, and another input parameter as slice are included in the diagram in the number of certain divisions. It should be noted that when drawing a two-dimensional slice diagram, when the graph of change in an output parameter is plotted according to one or two input parameters, the values for the other input parameters defined in the process of creating response surface method in drawing diagrams are not used. They must have a fixed value. This value can range from the maximum value of its range to its minimum value and can be manually defined. Now, suppose, for example, that changes in an output parameter as temperature outlet are investigated in terms of change in two input parameters such as length and radius using RSM method. Also, the other input parameters are equal to a constant value equal to their average value in the range of their changes. This figure shows a change in output parameters in output temperature, of course, in terms of geometric length and radius, so that the length parameter changes along the horizontal axis and the radius parameter is compared in pieces in 5 divided values. The local sensitivity bar or pi determines the rate of change of each output parameter for each of the input parameters independently. That is how sensitive each output parameter is to each of the input parameters. The relationship is related to the sensitivity of each parameter or output variables as follows. Thus, this percentage of sensitivity is equivalent to the ratio of the difference between the maximum value of the output parameter and its minimum value to the average value of that output parameter. If this criterion has a positive value, it means that the output parameter and the input parameter have a direct relationship. And if this criterion has a negative value, it means that the output parameter and the input parameter have an inverse relationship. The greater the degree of the sensitivity, both positive and negative, and the greater the number of 1 or 100%, the greater the dependence of the output parameter on that input parameter. The local sensitivity chart is plotted as a bar. The horizontal axis is the location of the measured parameter or output parameters. The vertical axis represents the percentage of sensitivity, and the colored bar in the diagram represents each of the input parameters. If the chart is plotted as a pie, a 360-degree circle appears, each of which has a larger fraction of a percentage depending on how sensitive they are to the desired parameter or output parameters. They occupy more angles. Suppose, for example, that the two output parameters change as the temperature outlet and the mass flux outlet flow, as the three input parameters of the length of the geometry, the radius, and the input velocity. The velocity inlet is investigated using the response surface method. This figure, the top figure, shows the local sensitivity diagram of the output temperature variable bars to the geometry length and radius parameters and the input flow velocity, so that the three colored bars represent the three parameters or the input variable, and the reason for the two-piece diagram is the study of the sensitivity criterion and the two output parameters. Now suppose that, for example, the two output parameters change as the temperature outlet and the flux outlet flow as the three input parameters of the length of the geometry, the radius, and the input velocity again. The velocity inlet is investigated using the response surface method. This figure, the bottom figure, shows the local sensitivity diagram of the output cycle variables to the parameters of geometric length, radius, and input velocity, so that the three color pieces represents the three parameters or the input variables, and the reason for the two-layer diagram is the study of the sensitivity criterion on the two output parameters. The local sensitivity curve represents the sensitivity of one or two output parameters defined in terms of input parameters or variables. In this type of curve, a constant value must be defined for each input parameter. In fact, in this curve, the sensitivity of each input parameter to the range of changes in the output parameter is shown. If using this curve, the sensitivity of an output parameter is measured in terms of a constant value of the input parameters. The vertical axis indicates the range of changes in the value of the output parameter, and the colored lines inside the curve represents each of the input parameters with their constant value. Also, the horizontal axis indicates the sensitivity according to the different values obtained from the output parameter. If using this curve, the sensitivity of two output parameters is evaluated according to a constant value of the input parameter, both horizontal and vertical axes indicate the range of changes in the value of the two selected output parameters. The colored lines inside the curve represent each of the input parameters with their constant value. In fact, in this case, the simultaneous changes of the two output parameters are shown together. That is, their simultaneous sensitivity to input parameters is measured. Suppose, for example, that the output temperature parameter changes have been investigated as the temperature outlet changes in terms of the three input parameters as the length, radius, and velocity inlet using the RSM. This figure shows the local sensitivity curve of the output temperature variable to the geometry length and radius parameters and the input flow velocity. so that the vertical axis indicates the change in the output parameter value and the horizontal axis represents the sensitivity of these parameters, and the colored lines for each of the input parameters are also inside the curve. Now suppose that the two output parameters are called temperature outlet and the mass flux outlet is changed by three input parameters called length, radius, and input velocity. The velocity inlet is investigated using the RSM, and this figure shows the local sensitivity curve of the two output temperature variables and the output mass flow to the geometry length and radius parameter and the input flow velocity, so that the horizontal and vertical axis represents the changes made simultaneously in the output temperature value and the output mass flow rate, and color lines for each of the input parameters are also inside the curve. The spider chart is a visual effect with a spider-like pattern that includes the range of changes in each of the output parameters. For each existing output parameter, an equivalent axis is created that divides that axis from its minimum value to its maximum value. The color part produced by merging these axes includes space for response points. Suppose, for example, that the two output parameters change as the temperature outlet and the mass flux outlet as the three input parameters of length, radius, and velocity. The velocity inlet input is checked using the response surface method, and this figure shows the spider diagram for the output temperature and the output mass flow at a constant value of the input parameters. As can be seen from the figure, the two vertical lines represents the segmented range of each of the output parameters and the color space for the expression of the response points. Master CFD experts are ready for DOE analysis, consulting, training, and CFD simulation. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.